Welcome to Earth's external features. So we already talked about internal features. Now we are going to discuss external features. And the reason is because what made these external features? It was the processes of the internal features that made them so. Earthquakes and mountains, growing because the plates are colliding, and then when the mountains grow, they can't last forever, so they have to break down. And so when they break down, that's called weathering. They get moved to a different place, that's called eroding, and then they get deposited in another place, and that's called deposition. And all three of those things working together make all of these, I think, pretty interesting external features of the Earth. Okay, so this is part 1 of 3. Your directions in Canvas tell you that you are not to turn in the note packet until its due date and until it's entirely full, until we've gone over all 3 of these PowerPoint presentation videos. Okay? So the first thing we're going to look at is weathering. And to weather means to wear down or to break down and change. Now, it doesn't mean to break down necessarily into something different, okay? It could also break down into just smaller pieces of itself. So both of those things can happen. Mechanical is the rocks and minerals breaking down into smaller pieces, like you see here in this picture. That is just a great big boulder that broke in half, and it's still, the left side is still the same material as the right side. But at the same time, it's chemical weathering, meaning that the rock's composition has changed. Now, maybe not the inside. You see this light part here? This is probably not changed, but you see how it's darker on the outside? It almost looks rusty. It's a very good possibility that there's iron in this rock, and iron oxide is the red stuff. So if there's iron in here, then it got transformed into a new substance. Its composition changed on the outside only. So this rock is an example of both A and B here, mechanical and chemical. We're going to talk about both of those. And there's a question actually in your notes, which I pretty much just answered. So which type of weathering do you think caused this rock to break in half, and then how do you know? So just fill in the blanks based upon what I said. If you missed it, you're going to have to go back. Okay, this is on YouTube. So the first one is called mechanical weathering, also called physical weathering, and it does not involve change in the rock's composition, only changes in the size and shape of the rock. So all of the things you see here are physical changes. So here the wind has eroded the rock away and sand blasted it off over many years, and it left this, what's called an arch or an arc. I think it's an arch. And then over here, this material has been broken down to smaller pieces. And of course, then it was eroded away down like little rivers. And then over here, this is an example of you start with a big piece, and the big piece gets broken up into medium-sized pieces and then smaller pieces. And the smaller it is, the easier it is to erode or move away. So weathering, erosion, and deposition in that order. Now, how does temperature play part in mechanical or physical weathering? Well, we don't have this too much here in Florida, but if you've ever been to a cold region, anywhere pretty much north of Florida, it snows and freezes every year. Sometimes it gets freezing down here in Florida once in a while. You get a couple days in January or February, but nothing that would do something like this. So what happens, water and you all know this, you've put water bottles in the freezer, and then you get it later and the bottom of the bottle's popped off, or a soda can in the freezer and the soda can explodes. So I think we've all experienced this in one way or another. But water expands. It's one of the very few things, one of the only things actually right now that I can think of that expands. Everything else contracts or gets smaller in volume when it freezes. Water is very special, unique, and in my opinion, a miraculous molecule that expands, and the percentage is 9% in volume. That's a lot, and it's very strong. It's all physical processes. So if that water freezes in a crack, it's going to expand and it's going to widen that crack until finally the rock breaks in half. You see the picture that actually happened on a rock on the right-hand side, and then the diagram next to it, and then the diagram below. These all show the process of this, and it's called frost wedging or ice wedging. Pressure can also, now of course the water freezing was also pressure, but it was caused by temperature. Here it's not freezing out, so plant roots can grow into the cracks, and the more the plant grows, the wider the crack grows, and then eventually it will break the rock right in half due to the pressure. And then of course rocks on top of rocks causing pressure on them to delaminate, to have their layers separate. These are all called exfoliation. It's kind of like the layers on an onion. If you've ever cut an onion or you've seen an onion, those layers that are in between, it's like that. And if you were to squish an onion, or you can probably try this at home, you can cut an onion in half and then put your hand on top of it and push real hard, the layers of the onion will exfoliate or peel away from the layers below. So that's what all these pictures are showing. So I've got a question for you about the picture on the left-hand side. This is how paper beats rock. So you're going to come back later and answer that question. And I just thought the one on the right-hand side was funny. That's an actual sign. I didn't take that picture, but I've seen falling rocks before, but this one actually shows falling people. So that's kind of weird. Chemical weathering now. We've moved on from physical or otherwise known as mechanical weathering, and now we're talking about chemical weathering. So when rocks are exposed to water, oxygen, which is 21% in the air that you're breathing right now, carbon dioxide, which is about 1%, a little bit less of the air you're breathing right now, and of course acid rain, and we're going to talk about all of these. So the interaction of those agents, and that's definitely going to be a question on your test, so you're going to have to pick, remember the agents of chemical weathering. These agents interact with the rocks, and they cause the rocks to break down chemically and become new substances. It dissolves the rock. You can see the chain on the top. Now that, of course, is a man-made substance. Well, the iron in the chain is not man-made. It was collected from rocks and then shaped into chain links. But that is an example of chemical weathering. But so are those rocks on the bottom. And we're going to see some more that happen right here in Florida. But I'm trying to save all the Florida stuff for the last PowerPoint because I think that's my favorite because it's kind of close to home. But one thing about all of this chemical weathering is that when the temperature goes up, the rate at which these rocks are chemically weathered increases as well, okay? So you can have the same exact substance in a cold region like Canada and then Florida, and it will happen faster in Florida because the temperature overall for a long period of time is warmer. So that pretty much answers this question. Will a car rust faster in cold weather or warm weather? And you're going to have to write why, okay, based upon that last slide. So you can finish that question later. It's a pretty cool picture, I think. How does water affect chemical weathering? So water can dissolve many types of minerals and rocks. Water is actually known as the universal solvent. It can break down lots of things over time, given plenty of time, maybe not overnight, maybe not the next day, maybe not even in your lifetime, but over thousands and thousands and tens of thousands and hundreds of thousands of years, water can do some pretty amazing things. So, because what it does is it breaks the larger molecules of the mineral down into smaller molecules of different kinds of substances. So water just sitting here in this pool will slowly chemically react with the things in the water, really, that chemically react with the rock and break it down in all these places. Oxygen, if there's presence of oxygen, this is how we know that oxygen was once in the atmosphere on Mars. But we learned about what happened to Mars's atmosphere. It got blown away into space by its magnetic shield going away in the core, created in the core. So its oceans and its oxygen, its atmosphere got blown away. But we know it was there because the rocks on Mars look like these rocks. We call Mars, I'm going to learn a lot more about this in the second semester, we call Mars the red planet, and it's really a brown-orange planet because of all the rust on the surface. The iron in the rocks turned to that brownish rust that we all know about. And that's called oxidation. Any reaction that oxygen is combining with something chemically, that's called oxidation. And again, I said this before, but the air that you're breathing right now is 21% oxygen. We'll learn about the concentration of other gases later, but so it's readily available to combine with rocks and turn them different colors. Not just iron. I keep referring to iron here, but there's copper in rocks that will turn the rocks kind of a greenish color, and others as well. If you look up at the periodic table, there's a lot to react with in this universe. How does carbon dioxide affect this chemical weathering? Okay, and this really comes down to Florida. That's why I have the example Florida down there. But when carbon dioxide combines with water, it makes a very weak acid. You could do this, you could show this in your home. Just take a glass of water from the tap and a straw and blow into the straw in the water. You'll make lots of bubbles and it'll sound really silly. But if you were able to test the acidity before, or the pH, same thing, before and after you blew into the glass, you would see that just because you blew in it, the carbon dioxide in your breath turns the water slightly acidic. Now, it's only slightly acidic, so it can only dissolve certain types of rocks. But rocks, especially with a mineral called calcite, which is found in limestone, is very susceptible to carbonic acid, meaning carbonic acid will react more readily with those types of rocks. And of course, virtually all of Florida's bedrock, all of the rock that you dig down deep enough, 10, 20, 30 feet in some places around the state, it's almost all limestone. And that's why we have caves underground, which we're going to learn about in this class. And that's also why we have sinkholes. You may have heard about sinkholes before. They are a little scary, but they're also very interesting. So this is what that limestone looks like after it's affected by chemical erosion. Chemical weathering, not erosion. Erosion's carrying away. Chemicals, weathering is breaking down, right? So that Swiss cheese looking thing, looks like the cheese with a bunch of holes in it, is limestone that was subjected to thousands upon thousands of years of soaking in slightly acidic carbonic acid water. And if you've ever been in a cave anywhere in the world, and you've seen stalactites and stalagmites, like you see on the right-hand picture there, those columns of rock, actually they're minerals, which make up rocks. Those are very highly calcite limestone caves that are all formed because carbonic acid is slowly breaking down the rock. So speaking of acid, how does acid rain take part in this whole chemical weathering? Well, acid rain is the result of burning fossil fuels. The more fossil fuels, oil, coal, and natural gas, which is the cleanest of the three, coal being the worst, the more we burn, the more sulfur dioxide we put into the atmosphere and nitrogen oxide, and these react in the atmosphere with water to make acids, sulfuric and nitric acid, just like carbon dioxide makes carbonic acid when it mixes with water. So these are stronger acids than carbonic acid. And when they come into contact with rocks, and a good example, if I showed you a natural rock, you probably wouldn't really be able to tell the difference from its original form. But if you look at a statue, which is a carved rock, okay, you recognize the shape on the left, but on the right, you can see after just about 100 years of burning fossil fuels, that's what happened to that statue. That's how much it chemically weathered. Virtually can't see it at all. And then when these acid rains come into contact with living organisms like forests or lakes, over time, not right away, when you're outside and it rains on you, don't worry, you're not going to get burned by acid rain coming down. It's not like that. It builds up in the environment over not too many years. It doesn't take that long, maybe 10, 20, 30, 40 years. It can change the acidity of the soil and kill the trees, or change the acidity of a lake or pond and kill fish. So here are some review questions. These are in your notes for you. 3 of them on this slide. Distinguish between the characteristics of unweathered rock and highly weathered rock. So you're going to have to write a little description there. Compare chemical and mechanical weathering, and describe the factors that control the rate of chemical weathering and those that control the rate of mechanical weathering. And they're all from the notes, and these are pretty much going to be questions on your test, okay? And that's the slideshow for part 1 of 3.